In this video, we're going to explore using our pH calculations in non-standard ways. So here's an example where we're going to add sodium hydroxide to a buffer. And what we want to know is the original ammonia concentration of that buffer. And we're going to solve it from just knowing the change in pH. Well, not exactly just knowing, but not having the normal information. So in this case, I know that my ammonia buffer was created by adding 25 grams of ammonium chloride into 1 liter of aqueous ammonia. Now, this is how you generally actually have ammonia. It's dissolved in water, and so you have some concentration of ammonia in water, and then you add other chemicals to it, and that's how you'd make your mixture. But we're going to pretend in this case we forgot to write down the concentration, or maybe it had rubbed off the bottle, or for some reason we didn't know the original ammonia. Well, to this 1 liter of unknown ammonia with 25 grams of ammonium chloride, we're going to add some sodium hydroxide, 0.0013 moles of it. And what happens is the pH changes by 0.031. That's the change, though. It's not the pH itself. That's just how much it alters by. So using this info, we're going to solve that original ammonia concentration. Let's think about how we do that for a minute. What's it mean? What's the delta pH? The change in pH? Well, that's just the difference from the original pH and the final pH. So that's got to equal the pH final minus the pH initial. Well, there's a couple ways we can solve pH. You could do the Ka is equal to the H plus initial, the ammonia initial, all over the ammonium initial. And you could do that for the final concentrations. And then you could take the negative log of that K, or of that H plus that you calculate out, and you could solve your pH. But an easier formula in this case might be the one that says my pH is equal to my pKa plus the log of my base over my acid. pKa is not going to be different. That's just the Ka log form. So pK is going to be the same for initial and final. All that's really going to change is if I want my pH initial, then I need my initial base and my initial acid. And if I want my pH final, well, pK is still the same, but I just use the differences in concentration. What's my base final? What's my acid final? I can plug this in here, and what we'll find is that 0.031 must equal the pKa plus the log of the base final over the acid final minus pKa plus the log of the base initial over the acid initial, which means I'm adding and subtracting pKa. So they actually cancel each other out. If you think about why for a minute, well, the change in pH only comes from the differences in the log values. The concentration of your weak acid and your weak base, as you change them and then let it equilibrate, causes your pH to change, but it changes around that pKa value. The pKa doesn't alter as we mix things, so if we're just looking at the change, it's only dependent on the concentrations of weak acid and weak base. And so 0.031 is going to equal the log of our final base concentration over our final acid concentration minus the log of our initial base concentration over our initial acid concentration. So we can think about these relations to pH for any given mixture, and we can say, hey, our original mixture would give us a pH for the original amounts. Our final mixture would give us a pH for the final amounts. Subtracting those two is going to give us the difference in pH. And so for a buffer, our change in pH is equal to the log of the final minus the log of the initials. So if we can find most of these, we can solve for the ones we don't know. Well, let's hold. Let's take a second and see if we can't find some of these values. We were told the amount of acid that we added. We had 25 grams of ammonium chloride. So this is the solid salt that you'd weigh out to add ammonium to a solution. When these dissolve, they fully separate, you get the weak acid ammonium, and you get a chloride, which is a non-basic salt. So 25 grams of ammonium chloride, it's about 53.502 grams of ammonium chloride in 1 mole. And there's 1 mole of ammonium chloride for every 1 mole of ammonia in that ammonium chloride. And so we actually find the amount of ammonia that we're going to create, which is 0.46727 mole of ammonia. Well, we're in 1 liter of solution. That was the original problem. So that's our molarity. Originally, we had 0.46727 molar ammonium initial. So we know 1 of these. Well, what about final? Well, we added sodium hydroxide. Sodium hydroxide reacts with the weak acid and consumes it. And so our NH4 final is going to equal the NH4 initial minus what we lost to sodium hydroxide. 0.46727 moles of ammonia originally, minus the 0.0013 mole that the hydroxide, which was the amount of hydroxide in this problem, that was added, will wipe out from it. That's going to end up with 0.46597 mole of NH4 plus final. We're in 1 liter, so we'll go back above. That means I now know my initial acid and my final acid. I know 2 of these. So let's plug that back in. Let's take our relation to solve for the difference in pH, and let's plug in some values. 0.031 must equal the log of the base final over the acid final, 0.46597, minus the log of the base initial divided by the acid initial, which was 0.46727. Well, one of the rules for logs, if we don't remember, is that the log of x divided by y is the same as the log of x minus the log of y. So logs have their own kind of conversion rules, and this is one of them, which means we can break this down a little bit into something a little bit more manageable. 0.031 must equal the log of base final minus the log of 0.46597. All that should be minus the log of base initial minus the log 0.46727. Distribute some negatives here, but we also have logs of decimal places. This one will be negative 0.33164. Log of 0.46727 is going to be negative 0.33043. And we're doing some subtracting of negatives. So we got to rewrite this, taking into account all the signs. 0.031 is going to equal, let's get rid of all these parentheses as we factor this out, the log of the base final. So negative, negative, subtracting negative is going to be adding it. So plus 0.33164 minus the log of the base initial, and then minus a negative. So 2 negatives for a positive, another negative for a negative, subtracting 0.33043. Well, I got a value here, and I have something I can subtract to the other side. I have something I can add to the other side to move it around. Let's first combine these two. 0.031 will equal the log of the base final minus the log of the base initial plus 0.00121. I can subtract 0.00121, subtract 0.00121. What we will end up with is 0.02979 is equal to the log of the base final minus the log of the base initial. We'll recombine these for a second. 0.02979 equals the log of my base final over my base initial. So we've simplified it down. We got rid of a lot of extra components, but we still have two unknowns. We want that base initial, but I also don't know my base final. However, I do know a relation between them because, well, I had some starting value and I added hydroxide. What's my base final? Well, it's going to be my initial base plus the extra gained from the hydroxide addition, so plus 0.0013 mole. When you have a buffer and you add strong base, it creates more weak base. It did it by consuming the weak acid. So earlier we lost some of our initial acid. We subtracted the amount of hydroxide. This time we have to add it because we're creating the base, which means I do have a relation here. I can figure out how much is going on. What is base final? Well, it's going to be base initial plus 0.0013. So 0.02979 is equal to the log of the base initial plus 0.0013 divided by the base initial. Well, I want to get rid of that log, so 10 to the, we'll make it go away, 10 to the 0.02979 must equal the base initial plus 0.0013 divided by the base initial. We'll find that 1.071 is the ratio of the final concentration divided by the initial. So it went up by 7.1%. Our base initial plus 0.0013 divided by base initial. So that extra from the hydroxide increased the top by about 7% more than the bottom, which is why the ratio is 1.071 instead of 1 if they were equal. Well, I can multiply base initial over, so 1.071 base initial will equal the base initial plus 0.0013. I can subtract one base initial from both sides. 0.071 base initial equals 0.0013. Divide by the 0.071. What we'll find is that my base initial is 0.01831. Now we could add the moles with our concentration earlier because we were in 1 liter. Our molarity was our moles. We kind of lost the brackets here because we didn't have to break it back down. Our molarity was our moles. So technically this is the moles, but it's in 1 liter. So the original base concentration was 0.01831 molar. Let's check that. Did we actually find it, or did we watch a 10-minute video that led us in circles? Well, let's check real fast. Initially, we said our ammonium, just from the 25 grams, was 0.46727. And we just now declared that our initial ammonia must have been 0.01831. So let's take those. Our pH is going to equal the pKa plus the log of the base over the acid. Negative log of 5.6 times 10 to the minus 10. Our pKa is going to equal 9.252. So 9.252 plus the log 0.01831 over 0.46727. That's going to equal our pH. And our pH initial, 7.845. What's our pH final? We're going to need to know the ammonium final, which previously we said was 0.46597. We need to know the base final. Well, remember, base final was base initial plus 0.0013. So 0.01831 plus 0.0013 for 0.01961. So our final ammonia after the sodium hydroxide addition should be 0.01961. Plug those in, 9.252 plus the log of our base, 0.01961, so our base final, over our acid final, 0.46597. That pH comes out to 7.876. Check those two, minus 7.845, we get 0.031. Our delta pH, if we have these concentrations, indeed, is what we expected it to be. So what we've been able to do with this problem was not simply be given a bunch of concentrations and figure out what our pH was, which is normally what happens if we attempt to make a solution. But especially if you're attempting to determine an unknown, say a bottle that had been mislabeled or you think is mislabeled and you want to check it. This is a way you can check for the concentrations of an unknown amount of your base. And follow up by looking at how it changes to double check the value calculated. And so we use the change in pH, related our pH calculations and how if we're at two different states, we could subtract them to find the difference. Took those log calculations, found some of the concentrations to cancel some of those unknowns out. Explored a little bit of log math. Log of A over B becomes log of A minus log of B. Spread those out so we could calculate out the known quantities, subtract them across to the other side so that we could get just the remaining two unknowns. Thought back and considered about those unknowns. Well, our base initial and base final are related through the amount of hydroxide we added, same as our acid initial and acid final. And so knowing that, we could get rid of one of our variables and take us down to just one from the original four. Once we have only a single variable, we had to rearrange and set equal to it. And we were finally able to find that the concentration of base initial that made it all work was 0.01831 molar. Granted with 2 sig figs. So 0.018 molar would be our concentration in the end.